Welcome to the presentation. So today I will talk about the main challenges in microgrid protection, the prevalent approaches for microgrid protection, and I will also elaborate on a PMU assisted scheme uh, for the same purpose. So here are the contents of my presentation. So let us have a look at the challenges in microgrid protection, in particular how microgrid protection poses different challenges from those in the legacy grid protection. So first of all, the fault current in the microgrid varies drastically between grid connected and islanded modes. The principal reason is that the equivalent impedance changes when the mode of operation of an MG is switched from grid connected mode to islanded mode and vice versa. Secondly, although microgrid lies on the distribution side of the conventional grid, yet the distribution protective devices such as fuses and recoillers they do not serve well for microgrid protection because of short circuit capacities, different short circuit capacities and fault current levels. So this leaves behind the traditional devices used on the transmission side such as directional overcurrent relays and differential relays etc. for MG protection. Issue in microgrid protection is the high penetration of distributed generation units. Typically, renewable energy resources or RES renders conventional protection schemes with no directional element ineffective. Next, we look at some capabilities that are required of the distributed generation or DG units in a microgrid. So on the right side, we can see a figure of a microgrid, which illustrates its salient components. So we can see first of all that there are two parallel feeders which are emanating from PCC, that is the point of common coupling. Then we can see SCEMS, which is a supervisory control and management system that communicates with local controllers. The local controllers are present on uh, each load and each distributed units. And we can see a variety of loads and resources here, such as wind, photovoltaic, combined heat and power, diesel and gas turbine, etc. Uh, okay. Requirement to withstand very low voltages. Now, the standard grid rules require that the RES units they remain connected to the main grid for the entire fault duration. This is known as fault ride-through capability. And the figure on the right-hand side shows a fault ride-through curve that RES units are required to follow in the European Union. So typically 150 millisecond is the time for fault clearance, and we can see that at least for one third of this time the voltage gets very low, and the requirement is that the connected unit should not be tripped if the PC voltage or the point of connection voltage stays above the curve shown. So far, one third of this 150 millisecond time the RES units are required to withstand these very low voltages. Another requirement is on the power factor. So we have the VSC interfaced system, that is voltage source connected interface system. It can measure the fault current angle. Uh, North American grid codes they do not distinguish between normal and faulty conditions, and they just impose a requirement that the power factor should stay above 0.95 for the positive sequence. On the other hand, the European grid codes require that reactive current be generated following a fault so that the voltage stability can be boosted. So we can see on the right hand side uh, that the gray area should be satisfied for even if a fault develops, the power factor should stay in this gray region, and this means that we may need to uh, inject reactive current. Okay, some core protection strategies for microgrid. So we have current-based methods. So typically, these methods use pre-calculated Thevenin's impedance of each source and then identify the fault section. And in case of an MG fault, if the MG or microgrid remains connected to the main grid, then the large fault current supplied by the main grid will help to selectively clear the fault. Then we have current and voltage based methods. These methods are based on impedance, reactance, and directional unit. Typically, impedance based protection schemes deployed at transmission level find their way into MG protection because they are free from fault calculations. Next, we have protection methods for microgrids that operate in islanded or standalone mode. So let us consider the essence of just one such method, which is based on inverter control and microprocessor relay. And a fraction of the fifth harmonic is injected into the fault current, and using software current control, which supports the microprocessor relay in accurately identifying the fault. Hardware hysteresis and software current control are used to protect the inverter against short circuit faults. Next, a microgrid can also operate in islanded mode when it is, like, say, disconnected from the grid. And one such method is presented in detail as the next in the next section. Okay, so here is the next section. So a phasor measurement unit or PMU assisted impedance angle based protection scheme for microgrid. So this method uses PMUs at both ends of the line to retrieve wide area positive sequence components of voltages and currents, which is then used to, these measurements are then used to compute integrated impedance angle, or IIA for short. And the authors report using a test bed which consists of a medium voltage microgrid 12.47 kilovolts and IEEE 34 bus distribution system. So these serve as test bed. So after extensive tests, the authors claim that their scheme provides protection against high resistance fault for various levels of DG penetration. And also their scheme, it makes the microgrid capable of operating in islanded mode. As I said earlier, that I am presenting this scheme as an efficient scheme for islanded operation. Okay, let us have a close look what happens to the IIA, or the integrated impedance angle, for internal fault in a microgrid that also included a distributed generated unit, or DG unit. So we can see a schematic in this figure. This is a two bus system to help us understand IIA, and it can, the results will apply on a larger system as well. So we can see two nodes. On the left hand side we have bus B1. On the right hand side the node 2 has bus B2, and in the middle the node 3 has the point where we will measure the fault, VF1. Okay, so on let us go through some terminology. So V11 is the positive sequence component of voltage at bus 1. V21, at this time this is again positive sequence component of bus 2. So the second one in the subscript indicates the positive sequence, and the first letter in the subscript, or the first digit in the subscript, indicates the bus number. Similarly, we have I11 and I21, which represents positive sequence component of currents at bus 1 and bus 2 respectively. ZA is the equivalent positive sequence impedance of source connected to bus 1, while ZB is the equivalent positive sequence impedance of source connected to bus 2. Sub D. Z sub D is the equivalent positive sequence impedance of the whole distribution line from B1 to B2. This distribution line has impedance ZD, and it is divided into two parts, ZD1 and Z sub D2. What is V sub F? V sub F is the positive sequence fault component, or the positive sequence component of fault voltage that occurs in this line joining bus V1 and V2. So we see its representation here. Okay. So as I said earlier, so the impedance is divided into two parts, ZD1 and ZD2. And going to the right hand side, so uh, SII, it is this ratio, voltage to current ratio, and we can again see some simplification, and then based on SII we can also find IIA, like integrated impedance angle, which is argument of negative of Z plus Z1 plus ZB over Z2. So what basically it means? So Z1 is equal to Z sub A plus ZD1, and what is Z2? Z2 is Z sub B plus ZD2 respectively. So if we examine these impedances, they will always stay positive, and therefore IIA, or impedance angle, will be negative for internal fault. Uh, so I have shown this equation for fault inception close to B1. Similarly, the authors have developed equations for IIA when the fault inception is close to B2 or in the middle. The conclusion is that for any internal fault, if microgrid contains a DG or it does not contain DG, the IIA is negative. This can help us to decide on relay operation. And similarly, the authors also derive that if a fault external to the microgrid happens, whether the microgrid includes DG or not, it will be positive. The angle will be positive for the external fault. So based on this, we have this operation diagram, and we can see that that relay can be set to operate whenever the angle falls negative. But what happens is, to avoid noise and stripping, uh, the authors recommend that integrated impedance angle of -5 degrees to +5 degrees is considered as dead zone. So this red region is considered as dead zone, and we do not, even if the angle is like -4 degrees and -4 degrees, we do not want the relay to operate based on extensive experiments done by the authors. For internal faults, the IIA values lies between -5 degrees and -90 degrees. So this range indicates internal fault, and the relay issues tripping command to the breaker. Conclusion: microgrid protection has challenges different from those of conventional grid. There are some requirements on the distributed and DG units and RES units during the fault, and then based on PMU measurements, uh, we can find integrated impedance angle, and the sign and the value of that angle can guide the relay to initiate protective action. So in summary, if the negative angle is more than -5 degrees, then we conclude that an internal fault in the microgrid has happened. These are my main references. Thank you.